Coming up on Extra Credit, we make paper rockets, meet an engineer who helps people explore outer space, and remember the life of an amazing woman known as the human computer. Stay tuned.
This program is made possible in part by Michigan Department of Education, the State of Michigan, and by viewers like you.
Hi, and welcome to Extra Credit, where we meet interesting people, explore new ideas, and discover fun places together. Each episode will introduce you to people who use math, science, sports, and writing to make the world an interesting place. My name is Mrs. Pizzo, and I'm delighted to meet you. Our theme today is space, but before we head to the moon, let's meet our co-host.
Hi friends, my name is Sarayu, and I'm so happy to spend this time with you. Have you ever thought about what it would be like to go into space? I definitely have. Did you know that there are some people who knew they wanted to explore space, even when they were little kids? Let's start by hearing about one such kid, Ron McNair, who later became a physicist and was the second African American to enter space.
When he was 9 years old, Ron, without my parents or myself knowing his whereabouts, decided to take a mile walk from our home down to the library, which was, of course, public library, but not so public for black folks when you're talking about 1959. So as he was walking in there, all these folks were staring at him because they were white folk only, and they were looking at him and said, who's this Negro? So he politely positioned himself in line to check out his books. Well, this old librarian, she says, this library is not for coloreds. He said, well, I would like to check out these books. She says, young man, if you don't leave this library right now, I'm going to call the police. So he just propped himself up on the counter and sat there and said, I'll wait. So she called the police and subsequently called my mother. Police came down, two burly guys come in and say, well, where's the disturbance? And she pointed to the little 9-year-old boy sitting up on the counter. He says, man, what's the problem? So my mother, in the meanwhile, she was called. She comes down there praying the whole way there. Lord Jesus, please don't let them put my child in jail. And my mother asked the librarian, what's the problem? Well, he wanted to check out the books. And your son shouldn't be down here. And the police officer said, why don't you just give the kid the books? And my mother said, he'll take good care of them. And reluctantly, the librarian gave Ron the books. And my mother said, what did you say? He said, thank you, ma'am. Later on, as youngsters, a show came on TV called Star Trek. Now, Star Trek showed the future where there were black folk and white folk working together. Right. And I looked at it as science fiction because that wasn't going to happen, really. But Ronald saw it as science possibility. Mm-hmm. He came up during a time when there was Neil Armstrong and all of those guys. So how was a colored boy from South Carolina wearing glasses, never flew a plane, how was he going to become an astronaut? But Ron was the one who didn't accept societal norms as being his norm. I mean, that was for other people. And he got to be aboard his own Starship Enterprise.
Here on Earth, we can use sunscreen to help protect ourselves from the sun's UV radiation. In space, there's no atmosphere to filter out the worst of it. So you'd think astronauts would fly around with an extra rocket full of SPF 50 to protect themselves. But it turns out, UV is the least of their worries. If we ever want to get to Mars, we're going to need more than a tube of coconut-scented grease. There is UV radiation in space. The sun puts out radiation along pretty much the entire electromagnetic spectrum, from radio waves to gamma rays. Starting around UV, electromagnetic radiation has the potential to strip electrons away from molecules and cause chemical havoc. If UV light hits a piece of DNA, that DNA molecule can break and cause mutations in our cells that can lead to skin cancer. Earth's ozone layer stops the most dangerous UV radiation, but some less dangerous but still kinda dangerous UV can still get through, and that's why we need sunscreen. In space, there's much less atmosphere, so you would think that astronauts would slather on the screen. But they don't, because spaceships and spacesuits are built out of stuff that stops UV radiation. So theoretically, there's more than enough UV in space to give you the worst sunburn of your life ever, but that's the least of your worries. The real worry for astronauts isn't UV radiation, but high-energy subatomic particles, plus stuff like gamma rays. The sun gives off both electromagnetic radiation and those high-energy particles, like protons, electrons, and alpha particles. Then there is the risk of, and we are not joking, atomic nuclei from stars that exploded a million years ago. These supernova remnants are called galactic cosmic radiation, and they're mostly protons and alpha particles, plus a smattering of heavier particles, tearing through space at nearly the speed of light. Don't worry about what all these things are. There is no quiz and no homework assignment at the end of this episode. They're just small things moving very, very destructively fast. And anything moving at such incredible speeds has a lot of energy and a lot of potential to break whatever it hits. That could be an unfortunate astronaut, but it's more likely to be the wall of a spacecraft, at which point some of those atoms could break apart and produce secondary radiation, more protons and alpha particles or gamma rays that might hurt the astronauts inside. Here at home, we really don't have to worry about this kind of space radiation. Far beyond the ozone layer, Earth has another radiation shield, our magnetic field. And those space particles can be deflected by a magnetic field. And the fact that our planet is a giant magnet comes in real handy when it comes to bashing most of those particles right back out into space. Fortunately, although astronauts in Earth orbit, like on the International Space Station, fly above our atmospheric UV shield, most of the time they're still low enough to be protected by our giant magnetic umbrella. The risk is to astronauts who leave the protective confines of our magnetic field, say to the Moon or Mars. A round-trip flight to Mars, plus a nice year-and-a-half stay, carries with it a radiation exposure equivalent to a roughly 5.5% increase in the risk of developing a fatal cancer. So any ship that travels outside of the Earth's magnetic field, including to Mars, would need extra shielding to deal with space radiation. The best way to block protons and alpha particles is with something of a similar size. That means that hydrogen, whose nucleus is really just a proton, actually makes a very good shield against high-energy space particles. That's true even though it's the smallest element. And that's good news for space travel, because hydrogen is really lightweight, and we'd have to take lots of it to space anyway, like in the water that astronauts will need to, live and stuff. The sun produces radiation all the time, but space also has weather of a sort. Solar flares and other events can cause radiation storms that astronauts would need to shelter from. So one proposed idea is to build a sort of bunker hidden beneath the ship's water supply to hide in if a solar flare causes a radiation storm. Plastics also contain a lot of hydrogen, so believe it or not, a plastic shield is a very viable way to deal with potential radiation. But any kind of physical shielding, even nice lightweight plastic, increases the weight of the spacecraft and the difficulty of launching it into space in the first place. So engineers are also interested in developing a mini magnetic field, just like the Earth-generated one that protects us, which would basically be a force field, which would be sci-fi as heck and really, really cool. But current technology requires a huge, heavy power source to generate a strong enough field, so it's right back around to the weight problem. Radiation is just one of the many huge hurdles we'll have to get over if we ever want to go to Mars. NASA and other space agencies do care about the safety of their astronauts. Plus, if interplanetary travel ever becomes a thing, and I will be first in line if it ever becomes a thing, the rest of us will want to be safe as well. Evidently, NASA hasn't considered that extra payload full of sunscreen, so we'll let them have that one for free.
I work in NASA Ames, and I am a space human factors engineer there. And what that means is that I build tools and systems to help people make space operations possible. Internships and summer programs are really, really important for girls and women. I know that the reason I work in NASA is because I had the opportunity to work in NASA one summer. And because I did that, I was able to understand what NASA's about, its mission, the kind of work I would be doing. And I got the contacts that I needed so that when I finished school and college and grad school, I was able to talk to these people and find a job in NASA. Girls should become engineers because we need girls. We need them to bring their creativity, bring their thoughts and their curiosity to the problem, because they can do it just as well as I can and anybody else can. I've been very fortunate to work in a lot of exciting projects, and as someone who is a bona fide space nerd, having the opportunity to experience all these things has been really, really amazing. I've done everything from using the same shuttle trainer as astronauts and learning about how they train. I've been as lucky as being able to fly in the parabolic flight where you can experience microgravity. But I think one of the coolest things that I've done is going to these analog field tests. So analog field tests are places around Earth that simulate some part of space exploration. So one time I got to go up to the Arctic and really explore and understand how scientists would explore an area kind of like Mars. And next week, I'm actually flying down to Florida because there's another Earth analog where the astronauts are living in a habitat underwater for 2 weeks. And they are simulating all different aspects of being in a mission and exploring another planet, being on time delay. You can't even talk to them real time. And so those kinds of experiences have really kept me motivated and excited about being in the human spaceflight program.
It's that time again, friends. I just received word that Dr. Blotch is going to check in with us to see how we're doing with our writing challenge. It involves creating comics. Are you ready?
Dr. Blotch.
Coming with the comics. Okay.
I'm totally here, Dr. Blotch. And so are you. How's it going? What's up?
Great, except I'm hungry for more stories via comics.
Oh, well, I mean, I'm working on it.
For me?
Yeah, that's exactly what I'm working on right now. It's funny that this is when you would pop in.
Let me see.
Okay. You know, it's not done because I thought I had a little more time, but...
You do have more time, but I'm anxious to see what you're working on, Courtney. May I please see your draft?
I'm gonna risk showing you this outline for my next page. Here it is.
Yes, pictures, yes. I see. Well, it seems like Sparkles is excited. Her Triceratops eyes are rather smooth, large right now. Her pupils are dilated. Yes, I like the little score marks that you've shown to indicate motion. Well, let's see. But by the time I get to the third panel you've drawn, I'm getting a little bored of Sparkle's excited face. I don't want her to not be excited, but isn't there some problem? You have to have a problem in a story, right? You have to have something that can be solved.
You know, you're right. I totally forgot about that part. I got really excited, hence probably why Sparkles is so excited. I was really interested in drawing the picture, so I forgot to give her something to kind of overcome.
Well, I can't blame you for that, because what is art except for an escape? I can't blame you for not thinking of problems, but, you can draw from perhaps, what if she's too excited? How would being too excited get in the way of her work and her relationships? I don't know, Courtney. You'll come up with something.
Look at me being inspired by Dr. Blotch. I'm totally gonna do my best. I'm on it.
Okay, so here's what we're gonna do. We're gonna do an activity, and the activity is called InPACT cratering. And what that means is that we're going to pretend that we're creating a craters on the moon from meteorites hitting them, okay?
We need a pan and
Some flour.
and we need that.
We're gonna use some crab boil. And we're gonna do this because we want it to be cool when we have our meteorites hit the landscape, okay? Hit the moonscape. Gotta have a lot of layers of stuff.
So as you can see, guys, my mom is pouring and I am shaking.
That's good. Now the next ingredient is let's do some cornmeal. Here, put that on.
Ooh.
Okay, that's good.
Yeah.
That's good. Now we just want to layer it over top. You don't have to shake it. But what you want to do is you want to show people what it looks like. So lift it up just a little bit.
So this is what it looks like.
Good. We keep a lot of seasoning in our house.
Yeah.
We want to use things that have like many different colors. Let's put a little bit of this baking soda over the top of it. I really don't want to part with this, but it's my coffee. I'm going to put a little coffee on top of it too.
Adios!
Here comes the fun part. Are you ready?
Oh yeah, wait for the meteor shower.
So, before we get into the meteor shower, you have to understand the reason why, what we're going to be looking for. One of the things that we learned when we went to the moon the first time was we learned that some of the craters have high ridges on the side. Some of them have deep centers, and they have a name for all of these different things. So we are going to be looking for 4 things. We're going to be looking for the floor. We're going to be looking for rays. We'll be looking for the ejecta. And you know what that is? That's the stuff that pops out and then lands on the other part of the surface. And we'll be looking for the wall. One little tip. We are going to be using a long cardboard tube when we do our craters. These are going to be our pretend meteoroids. And it's a meteoroid until it hits the surface. Then it becomes a meteorite.
Wow,
So see,
cool. Now we're going to use the small impactors. 1 regular speed, 1 slow motion speed. Now we are going to use the medium size impactor. So guys, we have a big marble. It doesn't even, a big impactor, it doesn't even fit in this thing. Look how big that is. So we're just gonna drop it. Hey guys, we are back, and my experiment exploded.
your experiment exploded your mind? Okay, so let's show everybody what we ended up with. We're looking for the floor of a crater, we're looking for ejecta, we're looking for the wall, and we are looking for the rays, okay? So we're gonna carefully take the impactors out. So let's identify some pieces now. We've got the floor, and then we've got like the wall. Can you tell me where the wall is on that one? Right there, very good, sir. We are looking for the rays. Now, I saw rays when we did the first one, when we did the first impactor. And then finally the ejecta. That's like all of the stuff that ended up everywhere outside of the pan and on top of everything else. Like, see, so we have a lot of ejecta on the floor.
Thank you, NASA, for making me do this project. I really liked it. Thank you.
Bye.
Bye-bye.
Welcome to InPACT at Home, where we practice interrupting prolonged sitting with activity. I am Melanie Rapelli, and this is my brother, Justin Strickland, and my friend, Landon. And we are here to help you get moving for the next 8 minutes. You'll be surprised at what these moments of movement can do for you and for the rest of your family, so you can stay active and healthy at home. So go ahead, get up, and let's start moving. For this movement activity, we're going to be doing a HIIT workout. You do not need anything for this, but if you would like a mat, that would work for one of the exercises, or the carpet is totally fine. Let's go ahead and get warmed up, start jogging in place. Get our heart rate up before we jump into our workout. Justin here will be doing the advanced version, so follow him if you'd like more of a challenge. And Landon will be doing the modified version if something is too difficult for you. Go ahead and follow him. All right, we're switching to jumping jacks. Getting our heart rate up. Nice job. And squat jump. Squat, touch the floor, jump up. Make sure you're leaning back on your heels. Nice job. Don't let your knees go over your toes. All right, and switching to walkout arm circles. So walking your arms out, back in, and arm circle. Go ahead and do it again. Walk your arms out, arms back in, and an arm circle. Nice work. Again, last one. Walking out, walking in, and arm circle. All right, jumping into the first exercise, we have candlestick roll star jumps. Landon, go ahead and show the modified version. Justin will be doing the advanced version. Here we go. Toes up. Nice, and we're jumping. Justin without his hands, toes up, and he's doing a star jump. All right, Landon, keep going. Nice job. Keep moving. Nice job at home. We're jumping. Justin's going. All right, good work. Keep going. His arms are up, and he's doing a star jump. Good work. One more. Nice job. Just get your toes as high as you can. Last one. Arms are up, toes up, and star jump. Good work. All right, we're resting. March it out. Stretch if you need to. Next one will be elbow hand plank. Again, follow Justin for the advanced version. Landon for the modified version. If you'd like a mat, go ahead and use the mat. All right, and we're moving. Elbow hand plank. All right, they're doing it on the hard floor. You got it. Nice job. Keep moving. Nice. Justin's doing his hands at the same time. Landon, elbow, elbow, hand, hand. Try not to wiggle too much at home. We're working our triceps, the back of our arms. Nice work, as many as you can. Couple more in there. Nice job. Go work at home. Feel the burn in your triceps. We're working. Go work, last one. All right, and we're resting. Active rest. You need to jog it out, march it out, stretch, twist. Get ready for the next one. We have crab tricep dip to opposite toe touch. Justin will slide the mat out of the way. I think we are finished with that. Get ready for dips with our elbows. Dip, dip, opposite toe or opposite foot. Dip, dip, opposite foot, opposite foot. So Landon, if you're watching, he has his butt on the floor when he's reaching. If you like a little bit of an easier version, if it gets too difficult, dip, dip, opposite foot, working our triceps and our core. Nice job. Couple more, we're reaching. And last one, dipping and reaching. All right, go ahead and stand up for an active rest. Moving in place. Next one will be plank jack, hip to hip touch. So we'll be starting in a plank and then touching each hip down to both sides. All right, here we go. Holding a plank, feet go apart, together, touch your hip, touch your hip. If you'd like an easier version, drop down to your elbows, apart together. Justin's gonna keep going on his hands. Nice job, keep moving. Good work, staying in that plank. We're engaging our core. Part together, hip to hip. Try to keep your core nice and tight. Good work, Landon. Nice job, Justin. Good work at home. Couple more, we got it. Nice, again, drop to your elbows if it gets too difficult. Good work, last one. All right, we're standing and resting. Active rest. Good work. Next one, we have a pike push-up. If you have a chair, you can put your feet up on a chair if you think you have a lot of shoulder strength. Otherwise, I'd recommend just staying on the floor. Your butt is in the air, or your glutes, and you are doing a push-up. You are working your deltoids, your shoulder muscles. Nice job, as low as you can go without falling on your head. Please don't fall on your head. Nice job, even if it's a little bend, that's okay. You should feel it in your shoulders. Nice work, Justin. Good work, Landon. Nice job at home. Keep it up. We're almost there. Good work, good work. All right, a few more. 2 more. You got it. Dip and dip. Nice job. All right, active rest, and we're moving. Good work, good work. All right, for our cool down, we are starting with some arm circles. Go ahead and move your arms backwards. The hard part is finished. We are cooling down. Nice work. Other way, switch. We're swimming. Keep swimming. Nice job. All right, go ahead and switch to shoulder stretch. Grab one arm, slight push on your shoulder so you feel a pull. And we're holding. Make sure to breathe. And switch. All right, and switching to tricep stretch overhead. Grab your elbow, slight pull behind your head. And we're holding. And go ahead and switch to the other side. And hold. All right, last one, we're reaching for our toes as far as you can. If you're reaching here, that's fine. You should feel a pull in your hamstrings in the back of your legs. Try to touch your toes the best you can and hold. Keep holding. Nice job. All right, good work. Nice job at home. We are finished. I hope you enjoyed today's movement break. InPACT at Home is a chance to apply the skills you may have learned in your PE class to improve your health. To learn more about the health benefits associated with daily movement, visit impactathome.umich.edu. Now don't forget to fill out your daily log. We will see you again during our next workout.
Support for this program is provided by the Michigan Public Health Institute and the Michigan Department of Health and Human Services.
Why do you like space so much?
There's so much sights to see. Nebulas, hot Jupiters, and supernova remnants.
Yeah.
They look so beautiful.
You know how I fell in love with space? My mom gave me a really cool space shuttle. You would wind it back and then...
Oh, I have that.
You have that? So I remember playing with that all the time and I wanted to become a pilot. I used to fly planes when I was 17 years old. And then after that, I started commanding spacecraft at NASA.
Have you ever been to space?
I have not, but it's a dream of mine.
I want to live on another planet.
Another planet?
Like, what kind of planet would you live on?
Of course, everybody's going to say Mars, right? You're going to say Mars?
No, Kepler 452b.
Oh, yeah. So Kepler 452b is your favorite planet. You know what we call those?
Exoplanets.
And there's actually, we estimate to be trillions of galaxies out there. So there's a lot of stars and a lot of exoplanets that we got to find. And so we need people like you to keep doing what you're doing. And it's one thing to get to this place where you know all this knowledge, but it's another thing to teach the knowledge.
Yeah.
So you were in kindergarten and you taught the 5th graders, right?
Yeah.
How did you like that?
It was a big opportunity for me. I taught all the planets. It was awesome.
How do you feel when we visit each other and we get to talk about space?
It feels good. I learned from you a lot. More than I could imagine.
You're my favorite person to talk about space too. You know that?
Yeah.
And you're learning so much by yourself too that you're teaching me as well. And that's really cool. The more you learn, the more we realize the little things in life we take for granted are the very things that make life possible. So when I look up in the stars, I think about that.
That is pretty cool.
My hope is that you are always going to be doing and learning about the things that you love the most. You can do whatever you want, but in the future, I think you're going to go to Kepler 452b.
I am an engineer at NASA's Jet Propulsion Laboratory in Pasadena, California. I work on the Mars Science Laboratory Curiosity rover. I am a systems engineer, and I've been doing a lot of testing for the past few years on activities that use the robotic arm, and we test them here on Earth in the Mars yard. I'm also training to be a rover driver and operate the robotic arm actually on Mars for the Curiosity rover. A typical day, I drive into work. I work at a NASA facility, the Jet Propulsion Laboratory, and we have a lot of wildlife, a lot of flowers. We're in the mountains there in Pasadena, California. We see deer. Sometimes there's been a bear on lab. That was a little scary. And then we go in and we first look at the data from Curiosity that it had acquired on the day before, on the Mars day, which is called a sol, on the sol before. Curiosity's typical day is that in her morning, she receives commands and instructions from Earth. Then she executes those. So she does all of the activities that we planned for her. She acquires a whole bunch of science data, images, things like that. Then that data gets sent back to Earth, and then we, the engineers, as well as the scientists, look at that data and decide what Curiosity is going to do the next day. So the scientists are looking at from a point of view of where do they want to drive, or what rocks do they want to explore in more detail. And the engineers were looking at to see if Curiosity is healthy and if all of the activities executed properly. And then we're also contributing constraints to the science team. We're telling them how much power they have and those types of things, and whether or not it's safe to do that. And then as a rover planner, I either plan specifically the commands for the arm, how to place the robotic arm on things, or how to sieve those samples and drop them off, or also plan the driving. And that's really fun because we get to put on our 3D glasses and look at the rocks, look at all the terrain and say, oh, is this rock safe to drive over? Do I want to, when I stop and I'm about to place the drill on a rock, do I really want to be perched up with one wheel on a big rock? I probably don't. So those are the types of things we're looking at, putting on those 3D glasses and feeling like we're on Mars almost. When I was growing up, I didn't necessarily think that women could be engineers. I think everyone told me that women could be anything they wanted, but I never saw anyone that was a woman and that was also an engineer until I went to college. And so I just want everyone to know that really it is for anyone. Anyone can do it, and don't listen to anyone in your school that's teasing you or telling you that things can't be the way you want them to be, because if you put your mind to it, you can do whatever you want.
Hi, my name is Mark from the San Antonio Museum of Science and Technology. Today, we're going to talk about rockets. What is a rocket? A rocket is an instrument that we use here to send things into space, such as like a satellite, maybe a rover, people. But what is a rocket exactly? Well, a rocket has 4 elements. One of them is going to be the nose. The next one is going to be the body. It's going to have some fins, and then it's going to have combustion. In order to build a rocket, you're going to need scissors, tape, a straw, pen or pencil, a ruler. Also, you're going to need a piece of paper, and you're going to draw a rectangle. It's going to have the measurements of 1 inch by 4 inch. And then you're going to have triangles. It doesn't matter how big is your triangle. You can make it smaller, you can make it bigger. You can have 2, you can have 3, or you can have 4. That will help you for your fin. Now, we start cutting our rocket. Let's cut the rectangle and then the triangle. Now I finished cutting 4 triangles and 1 rectangle. It doesn't matter how many triangles you want. I choose 4. Let's start building our rocket. The first thing you're going to need is your pencil to wrap it around your paper, kind of like a taco. Get your tape. The first part is done. Now, if you can't do it by yourself, you can always ask someone to help you. You get the second piece of tape and wrap it around on the top. Now that I have done the bottom and the top, let's do one along sides. What do you know? There goes my body. Now, the next thing I want to do is fold the tip of my body just like so. Grab some more tape. And there you go. Now you get tip. We use a straw because we want it to be smaller than the diameter that we use when we put it inside our rocket. To finalize this, we're gonna get our fins and we're gonna attach him to the bottom of our rocket. So grab your tape. Grab your fin. The fins are gonna be important for us to have. Why? Because they're gonna help us to keep direction. And there you go. I have one done. Grab your fin again. And now I have two. Now that I have finished my rocket, let's test it, shall we? I have a rocket and I have my straw. So you will put it inside. And when I test it first, 0 degrees. I don't have a protector. How do I do that? Use your hand, parallel to the ground. Ooh, let's see how far that goes. This is my feet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's test it one more time. What about 45 angle degrees? 45? How do I measure that? 0, 45. This time change. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Let's test it one more time, shall we? What about 90 degrees? Let's see what happens. 90. One, 2, 3, 4, 5. So as you can see, we tested different angles and with different distances. How fun was that? You can make it shorter, you can make it longer, one fin, two fins. You're the engineer, you decide. Have fun building your own rocket.
Hi everyone, I'm Mr. Lineberger and I'm so glad to be here with you today. There was this old commercial about candy bars. This one candy bar has chocolate mixed with peanut butter. If you didn't know better, you might not think those two would go with each other, but once you've tasted them together, delicious. In the commercial, someone accidentally gets the chocolate and the peanut butter mixed together. They're disappointed at first, but when they taste the resulting mix, they experience sweet bliss. Today's lesson is all about the chocolate and peanut butter of math. Our chocolate is division, and our peanut butter is fractions. Those are two awesome treats by themselves, but when you mix the two, you get sweet bliss. To stick with today's theme, today's lesson is going to be all about cookies. Let's start this party by thinking about fractions. Take a fraction like 1/6. What is a sixth, really? It's a whole divided into 6 parts, like this giant cookie I'm imagining. This cookie is so big, one person can't eat it all. You've got to divide it into 6 and let 5 other people share it. A sixth, then, is really just the whole divided into 6 parts. It's just 1 divided by 6. Did that blow your mind? 1/6 is another way to write 1 divided by 6. In fact, all fractions, if you think about them this way, are just division problems. Think of a crazy fraction like 2/77. That's just dividing something into 77 parts and taking 2 of them, which is the same as 2 divided by 77. We might write this as a formula of sorts. A over B equals A divided by B. If our fraction is 4/7, then we could write our formula as 4/7 equals 4 divided by 7. 2/11 would be 2 divided by 11. Are fractions just division? Yes, they are. Well, what about those fractions greater than 1? Yep, those are still just division problems. Take a fraction greater than 1 like 18/5. You can represent it as 18 wholes divided 5 ways, which is the same as 18 divided by 5. Or think about our formula. A over B equals A divided by B. 18/5 equals 18 divided by 5. No matter what, you can think of fractions as top number divided by bottom number, or numerator divided by the denominator. Time to get some cookies involved. Imagine I have 3 friends, so there's 3 friends plus me, that's 4 of us. We're splitting a box of cookies. If there are 20 cookies in a box, how many cookies do we each get? We could represent this as a division problem. 20 divided by 4 equals some unknown quantity of cookies. We could set this up as a partial quotient problem, like this, with 20 inside the box and 4 on the outside of the box. We could draw 20 cookies, then count them off for each person. Hey, we could even just open a box of cookies and count them out, which sounds like the tastiest plan I've heard so far. Or we could represent this as a fraction. 20 divided by 4 is the same thing as 20/4. If we simplify that fraction, we get the answer, which in this case is 5. How did I simplify that in my head? I just asked myself, what times 4 equals 20? 5. 5 times 4 equals 20. So let's make this just a little trickier. Imagine, instead of splitting 1 box of cookies with my friends, what if I split 7 boxes of cookies? How many boxes of cookies will we each get? If I think of this as a division problem, I want to divide 7 boxes by 4 people. 7 divided by 4 is the same as a fraction with a numerator of 7 and a denominator of 4. If I want to, I can stop there. Each of us gets 7/4 boxes of cookies. That's not very easy for me to picture in my mind, so I want to turn this into a mixed number. 7/4 is the same thing as 4/4 plus 3/4. So 7/4 is 1 3/4. That's easier for my brain. If we split the 7 boxes of cookies, each of us gets 1 whole box plus 3/4 of a box. Staying in this same line of thinking, what if we change our problem a little? Instead of 7 boxes of cookies divided by 4 people, what if we did 4 boxes of cookies divided among 7 people? How would we write that? If you said 4 divided by 7 or 4 over 7, you're right. And there's your answer. Each person would get 4/7 of a box of cookies. Let's picture what that would actually look like. Here's my box of cookies, like so. I'll divide it into sevenths. So that's 1, 2, 3, 4, 5, 6, 7 equal parts. Now, let's color in 4 of those. 4 sevenths. As you can see, if I divide my box of cookies in half, 4 sevenths is just a little more than half, so we're talking about a little more than half a box of cookies for each person. Let's wrap things up with one more problem. Imagine that I'm going to give these cookies to my class. I have 20 students in my class, and I have 32 cookies to give them. I have 4 jugs of juice to go with the cookies. So I put my class into 4 groups. First, how many students are in each group? Then we want to know how many cookies will each group get. Finally, how many cookies will each student get? There's a lot of parts to this problem, so let's break it down step by step. First, let's set up the groups. We divide 20 by 4 to get 20 students in 4 groups. Let's represent that as a fraction, 20/4. If we're satisfied with that, there's my answer. Each group has 20/4 students. I need an easier number to work with, but I know 20/4 is the same as 5. Each group has 5 students. Now I'll figure out how many cookies per group. I take 32 cookies and divide by 4 groups. That's 32/4. Each group gets 32/4 cookies. 4 times 8 is 32, so 32/4 equals 8. Each group gets 8 cookies. 4 groups, 8 cookies per group. The last part is knowing how many cookies per student. 8 cookies per group divided by 5 students per group. Each student then gets 8/5 cookies. That's the same as 1 3/5. So each student gets 1 whole cookie and 3/5 of another cookie. We can check our math by drawing a model. Here are my 8 cookies for the group. I can give a whole cookie to each group member like so. I'll divide the remaining cookies into 5 parts each. Now, when I want to give those out, each group member gets 1/5 of the first cookie, 1/5 of the second cookie, and 1/5 of the third cookie. That's a total of 1 whole cookie plus 1, 2, 3/5. 1 3/5. Sometimes drawing a picture really helps me understand the problem. Today we learned that division problems can be represented as fractions. The numerator is divided by the denominator. If you think of division problems as fractions, then often the answer is right there. My favorite fraction is that fraction of a cookie.
Amazing time exploring outer space with you. What did you think about Jessica's job as a NASA engineer? I loved it.
Thanks for having me.
Until next time.
This program is made possible in part by Michigan Department of Education, the State of Michigan, and by viewers like you.